System analysis and controls. What does that mean? This is what we're studying. What does a system mean? You could consider it as a combination of elements that act together to accomplish some kind of an objective. Now you can think of various systems. It could be your automotive suspension. In this case, I have this representative image. So this here is your spring and your damper, your disc for your brakes, your caliper, your A-arms, and so on and so forth. All of this is doing something that achieves a certain objective, right? And so the combination of all of these elements that are acting together, you could call that as a system. And to be able to analyze the system, you want to have a mathematical representation of that system, something from which you can then apply mathematical analysis tools to then derive some meaningful understanding of whether the system is going to behave in a certain way or not. And controls is when you are able to get the system to do what you want it to do. Okay, so we'll discuss these in a bit, but let's come back to this idea of a suspension system. Since I believe we are all familiar with it, the majority of us drive or have at least experienced automotive. And so, if this here is your real system, there are many different ways in which you can model this, from which then you can extract some mathematically meaningful uh, representation. And one way to model this would be to have a mass m of the weight of the car that is acting on this um, strut. And then you have the spring and the damper. And then you have a disk that is representing the interface of this wheel with the road, and the road might be moving in this way. The road might have some undulations, and that'll cause this disk to move up and down. And then you look at how it'll cause this mass m to bounce up and down based on the properties of the spring and damper. So this is one model. In this, you're not really accounting for how much the tire might deflect, because you're just assuming that a rigid disc is experiencing the road. But you could make the model a little more representative of the real world situation by having another representation where you have the same mass m, a spring, and a damper. And now you can have the mass of the wheel, or whatever it is that is going to move up and down. You have one mass here for that. That is actually called the unsprung mass. So it's the mass above over here is sprung by this system, while the mass here that is moving up and down with the road is the unsprung mass. Okay, this is just a discussion. It's not like we're really deriving anything at the moment. We're just talking about how you might be able to extract some mathematical representations from this. So already what we're doing is that this here is a real system. It's comprised of all of these components, which includes the bolts and all the fitments that are required to connect these things together. There's some flex that's happening here. We can maybe ignore all of that at a very fundamental level. If you're just starting out with analyzing the system, you can just start with this. And you can add one layer of complexity by now accounting for the mass of this unsprung mass as it moves up and down. And then this here, this spring would be representative of how much deformation the tire can actually take. And so now this roller is experiencing the road, and there's another model. Now you can go a level further and keep on adding layers of complexity, but in the end, a model is a conceptual representation of a real world system from which we can then extract something useful for our analysis. Okay, so this is just an example, but a model can be said to be a conceptual representation of a real system. And just so that we are complete, we did talk about what is a system in itself. A system would be a combination of elements that act together to accomplish some objective. Okay, so we've been talking about this. Now, this idea of having a model as a conceptual representation, it basically simplifies the real world system into what is useful for us, and it allows us to build an equation or a mathematical representation, which we will soon get to, hopefully by the end of this lecture. And it is built as a composition of different concepts, observations, notions, physical laws, which describe the system from its fundamental or primary ideas and elements. Okay. So in engineering, these concepts are formalized through physical tools such as, you could have a scaled prototype and you can actually do a test. So, for example, if you're in aerodynamics, you might have a scaled model of your full scale aircraft, and then you put that into a wind tunnel, and that is again a model. It's a representation of that real world system. And now, when you have it in a scale of, say, 1 is to 10, you then have to account for the Reynolds number to be able to make use of your results from experiments to actually make decisions for your full scale aircraft. Okay, that's just a conversation about how it can also be a scale prototype. But in this class, we're going to be working with it as uh, mathematical equations, in particular called equations of motion or governing equations. So we arrive at these equations after analyzing our system. And from that, we can then extract some meaningful information. Okay, so that's kind of what we're going to be doing. Now, as you can see, for this very simple system, we already talked about two different models, and we saw that we captured more complexity in the model. Of course, the more you can capture, the more accurate your representation is going to be to the real world system. But when you do have more complexities, it is more computationally demanding, more difficult to analyze, and so on. So, usually, you choose a model that is sufficient for your work. And that's why modeling is often considered a form of art, which means that your knowledge of the system, your experience, and also your personality, it affects what is the model that you develop. Okay, so you can think of it as a painter painting a scene. Okay, so for example, let's say Monet, he sees a view of a bridge and he paints it in a way that is representative of his experience of viewing that. So the shimmering of the light and the saturation and everything might be different from someone who just viewed it in passing and didn't really observe these things. Okay, so it's a form of art in itself. And why do we need to be modeling? What is the reason to develop these models? Um, as an engineer, when you make a new design or technology, you want to have some kind of a notion of how it's going to behave. Okay, and you want to be able to do that even before you have a prototype. So I'm currently listening to the book uh, How to Build a Race Car by Adrian Newey, and it is a lot of information about how you start with just sketching what is in your mind and you have it down on paper, and then you conceptualize that and look at it from the whole system's perspective, and then you look at whether it's going to achieve your objective, and then you can then have a consensus with the entire team that okay, this is a good design, or maybe there's a pointless design. If it's pointless, you discard it. But an initial model, which is simply maybe a sketch, it allows you to have a conversation and discuss about these new designs and technologies without actually building a prototype. Your prototype becomes a real world model, or a scaled prototype becomes an experimental basis for you to be able to make decisions about your final system. Okay, so why do you want a model? One thing is that you can treat new designs and technologies without a prototype, so it's cheaper. Also, a lot of times you are unable to disturb the operation of an existing system, right? So there's a joke, I think, in a mechanic and a cardiovascular surgeon are having a beer, and the mechanic is speaking about how he completely disassembled an engine and then um, was able to put it back together, and now the engine is running. And the cardiovascular surgeon laughs, saying that, okay, try doing that while the engine is still running, which is basically the job of the cardiovascular surgeon. And so he or she has a much more challenging job. And the same can actually be said about the electric infrastructure. So the entire electricity grid is, one, it's aging, it's built in the 60s in America, and two, it is continuously run because you cannot afford to lose power anywhere. And so you want to be able to do these restoration actions and upgradation actions without actually disturbing the system. And the only way you can do that is by having a model of the system. Okay, so you don't disturb the operation of an existing system. A level above models is actually the idea of digital twins. There's just a conversation um, wherein you tie in measurement data as well from existing systems into your model, and then your model is acting as a digital twin or a digital representation of the system. So that's more of a buzzword. The technology has existed for a while, but digital twin, blockchain, all of these buzzwords keep coming up, especially if you're active on LinkedIn. Um, so I guess this here is one aspect of why you want a model, because you can design even if the system is not available or it's active and cannot be disturbed and so on. It also helps you gain insights about the system. So gain insights and a better understanding. So the book that I'm reading right now, he talks about how in the 70s and 80s, everything was done by hand. You had hand sketching and hand drafting. And so a lot of times you wouldn't be able to, or you didn't have the time to be able to draw an assembly of all of the items together. And then when you actually build a system, you would find that things were, interfering with each other, and things were not as planned. Today, with all our modern technology and with all the tools that we have, we can analyze the system. We can see how the motion is going to be. You can see that everything is set up in the way that it should be. And so you are able to gain insight. You can analyze it. You can understand if it's a stable system. Is it going to behave in a way that will come back to its equilibrium position, or is it unstable and it'll go far away and break? Okay, so all of these things you can do by modeling and then analyzing your system. So if you're able to do experiments, then you can develop a very strong, well, you could say that it's a model that you can trust, because you validate your model and then you can extrapolate the results of that model to regions that you have not yet explored. Okay. Um, all of this is just a conversation. There's nothing like serious in the sense that you have to be taking notes and so on. Um, and okay, let's also talk about how it might be useful where safety is an issue. So you don't want to have experiments that are dangerous, for example, in nuclear reactors and so on. You don't want to unnecessarily expose someone to you know, radioactive materials and so on. So useful when experiments are dangerous, or when there are some extreme situations like firefighting and so on. You can use models as a way to simulate the real environment. For example, a firefighter. So you can use that for training for extreme situations and so on. So in general, when you're trying to build a mathematical model, you start with a real world problem that you're interested in. So this is what exists in the real world. And then you want to build a mathematical version or a mathematical representation, because then you can analyze the system and obtain a solution, right? So you have a mathematical solution, which you then analyze and interpret. And once you have that, you can then look back to see how this really relates to your real world problem. Maybe you missed something. Maybe there was some phenomenon that you didn't actually capture. And you can then return to this and restart the process with an updated understanding of the real world. Okay, so if you were to look at what's happening from here to here, you're taking the real world problem and then looking at what do we really understand about the real world problem? Why are we going to build a mathematical model? What kind of physical properties or governing phenomena or mechanisms exist in this real world system? Um, Further, what kind of a model do you want as a mathematical representation? Is it going to be, the simplest possible model? Is it going to be this one? Or maybe you want to have all four wheels of the car. So you have one more here, and then you have one more over there, and then you have one more over here to create your car's body. Is that a sufficient model for you? So these kind of questions, and how accurate should your model be? What kind of data is available? Do you actually trust the data that you're getting from here? All of these things come when you're converting your real world problem into a mathematical problem. When you're going from a mathematical problem to your solution, you want to look at which among the variables are going to be used to actually represent the system. So is the model going to be solvable if you choose those variables? What technique? Do you have an analytical method that will give you the solution, or do you have to use a numerical method to be able to find the solution? And further, what kind of representation do you use? Is it time based? Are you looking at how time evolves, or how is it going to be? Is it based on the frequency of some vibrating input? All of these things have to be considered. Okay, and then from this to this, you're now looking at what is the resulting structure that you're obtaining from the model, and can you actually verify your model implementation in some way? Can you run a test maybe? Does it correlate with the available data? So if you know about like machine learning, then you have training and testing data. So is your data that you used for training matching with the validation or the test data and so on? Okay, and once you have this, the final outcome here, you come back to here, and then you see, is your model too complex or too simple? Are you not able to actually make some meaningful out result from your analysis? And how will you use your results? And can the model be updated in some way based on the data that you have now obtained? Uh, is there a way for you to continuously update the model, perhaps using data? Then you'd be closer to a digital twin and so on. Okay, so this is the kind of process in this art form of modeling. And I guess at this point, we've talked about system and analysis. Now, what is control? So in this, let me use a few examples. So I'm going to bring in some pictures. You must have heard about cruise control. At least I trust you've heard about this. If you've not experienced it yourself, you have a vehicle that is now being driven on some road, and you have an objective of maintaining a certain speed, at the speed limit, perhaps. And so you set that to your uh, cruise control target, and now your vehicle must go at that speed regardless of whether the road is undulating, so whether it's flat or it's increasing in slope or decreasing in slope. Your controller is responsible for being able to maintain your vehicle at that speed. So depending on the aerodynamic resistance, the slope, the tire rolling resistance, and so on, your controller has an objective of managing the behavior of this system, that is the vehicle, to meet the requirement that is set by you, the user. Okay. Let's take another example from an automotive system. Uh, you must have heard about anti-lock braking systems. So vehicles have to have ABS, anti-lock braking systems, since I think at least 25 years or so. And the reason for that is that when you have ABS, there's a controller that modulates your braking so that if you're braking very harshly, your wheels don't lock. Because if they lock, then you lose control because your overall friction changes from static to dynamic friction. And so then you're not able to control your car as well as if you're able to prevent the wheels from slipping, which is what anti-lock braking does. So it's a control system that looks at the rotational speed of the tire, and if it sees that the tire is locking up, then it immediately modulates the brake so that it allows the tire to regain contact with, well, regain grip with the ground, and so on. So that's again a control system where you have analyzed the behavior of the system, in this case, a braking system, and it is able to use a combination of hardware and software to manage this behavior to make sure that the wheels don't lock up. Can you think of some other control systems? It is all around us. I ask you to just pause and think for yourself. But in the very room that you're sitting in, there is a control system, in most rooms at least. If you have an air conditioner, it uses a thermostatic control. So it is checking whether the temperature is above a certain temperature. If it is, then it turns on the cooling. And if it's below, it does not turn it on. So that's like a very simple controller. So again, it is managing the behavior of the system. In this case, the system would be the room. So to put this down in words, I would say then that a control system is a device that manages the behavior of a system so as to attain a specific performance target or requirement. Okay, well, by device, it's generally a combination of both hardware and software. Okay, so this is just a bit of a preview of what is to come in this semester. I hope this is exciting. It really is an important aspect of being an engineer to be able to take a real world system, develop a mathematical representation from which you can then analyze and then make some informed decisions about how your system should be deployed. And further, to be able to develop a control system that gets it to do what you want it to do. Okay. So in this class, we will be first looking at some essential components that represent mechanical systems, electrical systems, fluid systems, and so on. and then developing these mathematical tools from which we can then analyze the system and then make some predictions about its behavior. And then we'll get into designing the system and the controls and so on. Okay, to start with, we're going to deal with translating systems. And now, if you want to, you can start taking notes. Um, as you know, I'm not going to be sharing these notes since if I do that, then everything is passive. You need to be active in your learning as well. Um, we start with the concept of springs, which I know is familiar. So springs, they deform elastically when you're subjecting it to a force or some load. And when loaded, it stores the potential energy, and when unloaded, it releases that potential energy, returning to the equilibrium. Okay, they are shown in this way. That represents a coil spring. Um, they follow the Hooke's law, which says that the force in the spring is going to be proportional to the net deflection in the spring. So x2 minus x1, if we say that this here is moving to the right by x1, and this here is also moving to the right by some, in this case, x2, then the net deflection in the spring, which is like how much is the spring being deflected from its equilibrium position, that would be x2 minus x1, the deflection from equilibrium length, I should say. So spring, when it is being subjected to no force, it has, this as its natural resting state. Now one end is moving to the right by x2, other is moving by x1. So the net deflection is x2 minus x1, assuming x2 is greater than x1. What if it was the other way and this direction was x2? Then what is the deflection? It will be x1 plus x2, because that is the net deflection from the equilibrium length. Okay, so the Hooke's law says that the net force within the spring is going to be proportional to this, and there is a constant. It's given by k times, well, k is a constant, that is the spring constant, and in general it'll be marked with the spring as shown here, so k. So this constant is such that the net force is going to be k times x2 minus x1. Or this here, the net deflection can be given as delta x. So what does that mean? It means that if you were to draw on the right hand side delta x, and on the vertical axis you have the force in the spring, then this is going to be linear, and that slope is going to be slope k. Of course, this is an approximation. In reality, your spring will not have perfectly linear behavior. In fact, as your delta x increases, it'll be slightly exponential. But in this class, we are restricting ourselves to this region where it is linear. Okay, so in this class, we are idealizing the spring such that the force velocity, sorry, the force deflection relations are linear. Okay, I guess I'll write that here. They're linear, which means that force displacement or force deflection relations are linear. We also say that it is massless, which basically means that the force that's being transmitted is unaffected by the inertia of the spring. We'll get to that in a bit. But it means that your spring in itself is not contributing to inertia in the system. They're also passive, which means that they are not generating energy. They can store and dissipate energy. Okay, this is the ideal spring, which is what we're going to deal with in this class. Um, okay, so what does this here mean? I know you're familiar with this. Um, if you think about holding a spring between your hands and then you were to extend one side to the right, now your spring is experiencing tension. Well, I should be more clear. If you were to elongate the spring, holding it between your hands, let's say that your right hand pulls it to the right, your left hand pulls it to the left. Now, imagine this spring in your mind and you're pulling it outward. It is elongating. And so this force is going to try and restore it back to its equilibrium position. On the other hand, if you were to try and compress the spring between your hands, that is, your hands move closer together and your spring is essentially compressed, then your force that the spring is going to be generating is going to try and push the spring outward back to equilibrium. Okay, so if it's trying to push outward back to equilibrium, your hands are resisting a force that is acting outward. On the other hand, when you are elongating, the force that your hands are resisting are going to be trying to pull your hands inward. Okay, so in essence, this force Fs is the restoring force. It is proportional to the relative deflection and it tries to um, return the spring back to its equilibrium position. Okay, so let's just try to deal with a very simple system where you have a mass m and it's attached by a spring to a wall. Now, if this is a natural resting position, what that means is that there is no deflection in the spring. Okay, but let's say that you moved this mass m to the right. And we're essentially considering this mass to be a particle, that is, its entire position is defined by just one measurement. So let's say that we are measuring, meaning we only care about its position, we don't care about its orientation and so on. And this throughout the case where you have mass spring dampers in this course, we're going to be dealing it as just a particle where its position matters, but its orientation and the angles do not matter. So let's say that from its equilibrium position, so I'm going to mark EP, we were to move it to the right by some distance x to mark the same position I'm marking it here. So when you've drawn a reference as shown here and then you mark an arrow to the right, it means that when you're measuring to the right, your measurement is positive. If you were to measure to the left, your measurement would be negative. Okay, so in this case, what is the net force that this spring would be exerting as this mass has moved to the right? From the equilibrium position, this spring has now been elongated by x, which means that in this case, Fs is going to be k times x, and we can say that it is in tension. What does this mean? If you were to draw now the free body diagrams of the different components of the system, I highly recommend doing it as an exploded view so you have everything available. This mass m is here and this here is a spring k. This is going to be in tension, which means that this Fs is acting in both directions as shown here. Why is it equal? Why are they same Fs on both sides? Think about it. You've probably drawn this a few times. Why is this the same? That is because this spring here is massless. And so if you were to have the sum of forces in the free body diagram is equal to the sum of forces in the kinetic diagram, which I hope you're familiar with, the kinetic diagram accounts for the inertia, then because there is no inertia, on the right hand side will be equal to 0, which means that the net forces on the spring must be equal and opposite, which is why this here would be equal and opposite. Okay, let's now look at the reaction force. It will be the same Fs that is acting on this mass here. Are there any other forces on the mass? Yes, there would be gravity, that is mg, and there would be a normal force from the ground that is acting in this way. Any other forces? In general, unless I provide the specific details, you can assume that there are no friction components and there are no aerodynamic effects to consider. Okay, so just a general statement. Unless provided, ignore them. So this here is the free body diagram for the system. So you have the system being defined as the mass and the spring. And now for every component, you have first drawn an exploded view, and then you have looked at all of the forces, and you now have arrived at this. In the kinetic diagram, you want to capture all the inertial forces, which for the spring, it does not exist because the spring is massless. So you don't have to draw anything for the spring. Now the mass, on the other hand, it does have inertia purely by the fact that it has mass. And by Newton's laws, you have that you will have mx double dot, that is mass times acceleration, appearing in your inertial diagram. Now, in what direction should you draw that? Always remember that it only depends on how your x is defined as positive. Okay, so if x is positive in this way, then x dot is also positive in this way. That means your velocity is going to be positive in this way. And your acceleration is also going to be positive in this way. Why is that? That's because if you look at the velocity, that is x dot, it is limit delta t tending to 0, delta x over delta t. And this delta t is positive. So the only case where x dot would be positive is where delta x is also positive, which means it would be going in this direction, which means that your x dot is positive in that direction. Okay, you can do the same thing for x double dot, that is a differentiation of x dot. And so that means that if x is positive in this way, x dot and x double dot are also positive in that way. Okay, so if your x dot is positive in that way and x double dot is also positive in that way, then you have the inertial force as mx double dot, as shown here. Okay, so what can we derive from all of this? Well, using Newton's law, you have that the sum of forces in the free body diagram is equal to the sum of forces in the kinetic diagram. And to be able to write these vectors, that is, I mean, you know that forces are vectors, right? So you need to have some unit vector that you can use to represent the direction aspect. So you have, let's say this here is some nx hat unit vector, and this here is your ny hat unit vector. In this case, you can then write that the sum of forces is for the mass. Here, the sum of forces is n minus mg along the ny hat direction. plus you have minus Fs in the nx hat direction. Why is it minus? Because this is pointing to the right while the force that's appearing on that block in the free body diagram is to the left. This much is equal to, and on the kinetic diagram side, you have mx double dot along nx hat. Now, if you were to take along the ny hat direction, if you were to take a dot product, then what you'll obtain is that n minus mg is equal to 0, from which you then have n is equal to mg. And if you were to take the dot product along nx hat, you will have minus fs is equal to mx double dot. But we already defined what is the value of fs. So here, when you're writing this down, you are generally defining a positive quantity, or at least you assume that it's a positive quantity. And because this here is a positive quantity for x increasing, it is in tension. And so now you have, based on the directions, and you have minus fs is equal to this. You just substitute what is fs, which is essentially minus kx is equal to mx double dot. And if you were to now rewrite this, you get mx double dot plus kx is equal to 0. This here is the equation of motion for your system. Or your governing equation. And it is a mathematical representation of your system being in this configuration where you have a spring that is connecting your mass to some immovable wall. And so when you have the mass move to the right by x, this is how your system will behave, which means that mass times acceleration plus k times x is going to be equal to 0. And this is a rule that your system will follow. It's an equation of motion. It tells you how the system is going to behave. Okay, so we're going to look at this in detail, how from this you can get to your actual x. That is your x going to change like this? Is it going to change like this? How is it going to behave? That is part of the analysis. Okay, we'll get to that in, I believe, 2 classes. I hope that this stuff here is somewhat familiar to you. If not, let me know. Send me an email. Okay. Okay. What happens if there was a force that was acting on the system, and let's say that that force is acting to the left? Okay. I'm gonna remove this now because that was a representation for visualization. So this here means that x is measured positive to the right. In general, only this much will be shown. You understand that x dot and x double dot are also in the same direction. Let's say that the force was acting in this way, to the left. What changes now? Do you have to change this because your force is acting in this way? No. Your inertial force will only be dependent on what is the positive direction of your acceleration. Okay, it accounts for the reference system from which you're taking the measurements. The only change that will happen is that your force F is going to feature in your free body diagram. Now, at this point, based on this discussion, this might seem very elementary and a stupid point of discussion, but you should know that the most common mistake I see is that students ignore the direction of positive x and simply choose the direction of F in your inertial diagram or your kinetic diagram. Okay, so keep that in mind. When you're drawing the kinetic diagram, you're ignoring any of the forces and you're only looking at what is the sense of measurement in your system. So at this point, we have a new force. And since I'm lazy, I'm just going to do the whole thing in the same representation or the same system. So it's minus Fs. Is it going to be minus F or plus F? It's going to be minus F. And the reason for that is this force F is acting in the opposite direction to nx hat. Okay, so now your equation of motion is going to change because you will have now that it is minus Fs minus F is equal to mx double dot. And so when you replace Fs with kx, you then get this. And if I now rewrite this, I get this as my new equation of motion. Again, we want to have a particular style of writing this equation of motion wherein everything that's external to the system, that is in this case F, should feature on the right hand side. So the system was the spring and the mass, right? So this here is the system, and acting on that system is this F. So that's going to come on the right hand side. And now this style is good to have because it means that anyone looking at your equation can immediately know that this here is the input to the system. And everything over here, it describes the system. For example, M is a parameter that defines the mass. K is a parameter that describes the spring constant. X is the variable that is shown here. Now this minus sign denotes that the X is in the opposite direction to F. Okay, and with that, we will then move on to another component. So we've been describing springs. Let's now look at dampers. So a damper, it may be a little counterintuitive to you, but a damper has a restoring force that is only proportional to the relative velocity. They're represented as shown here. Where you have a coefficient C that represents the restoring force that's given by Fd, which is now dependent on the relative velocity across the ends. So if the right side is moving to the right by x1 dot and the left side is moving to the right by x2 dot, then your restoring force is proportional to that relative velocity across the ends, and the coefficient that makes it an equal sign is given by the damping constant or damping coefficient. Let me just make sure that I also wrote it for the spring. Well, I didn't write it, sorry about that. This here, K, is the spring constant. So in this case, you have a damping constant, a damping coefficient, where it is C x2 dot minus x1 dot. That becomes your restoring force. So in this case, you can write that the restoring force is proportional to the relative velocity across its ends. So this here is a damper in its mathematical representation, but what does this physically mean? Springs are probably very intuitive for you. You've probably played with springs where you have maybe disassembled your click ballpoint pen, and then you have a spring in there, and when you know that when you compress it, it'll push back, and if you elongate it, it'll try to pull inwards. That is actually modeling the restoring forces within the uh, metallic lattice. So usually spring steel and so on. They have, so it's whatever material it is, if it has a tendency to bounce back to its equilibrium position, you can then say that that is modeled using a spring. It doesn't necessarily have to have this coil structure. This is just a representation for the case where something that was of a certain length, you elongate it and it comes back to its equilibrium position. You compress it and it comes back to its equilibrium position. That is modeled by a spring. A damper, on the other hand, is a way of modeling a source of energy dissipation. So it's source of energy dissipation. So, for example, if you have parasitic losses due to friction or some chemical reactions and so on, this would be captured using a damper. And as you can see, the force that is there is going to be proportional to the relative velocity across the ends, which means if this end was fixed and this was moving to the right by x1 dot, then that force would be just Fd is equal to c times x1 dot. It does not care for what is the relative displacement. It only cares for what is the relative velocity. Okay, so keep that in mind, and I'm going to write that in red. A spring restoring force is given by Fs in this class is independent of delta x dot, that is the relative velocity. It depends only on delta x, that is the relative displacement or the relative deflection, while a damper's restoring force Fd is independent of delta x, that is the relative deflection or displacement. Well, I guess to be more accurate, it would be the deflection or relative displacement. Okay, so keep that in mind. Why is it shown in this way? It's because the shocks at the fundamental level, they are dampers, and essentially they have a piston within a cylinder, and this cylinder is filled with fluid, and there are holes in this piston, and as this piston moves up and down, it resists the motion, and it only resists the uh, relative velocity. It doesn't really care about whether the piston is above or below. Okay, so for now, this here is a mathematical model. Again, it is linear, which means that it is um, it doesn't follow a quadratic or any other relation with the relative velocity. So it is linear. It is also massless. It is also passive. Okay, in this class. Let's now look at an example where we have a spring, a mass, and a damper. Okay, so this is mass M, K, and C. And let's say now that we're measuring leftward as positive, and you have your force F acting on it to the right. Okay, in this case, we can think of this as a top view, and all of this is on a flat surface, and so mg would be acting inward, and the reaction, the normal force, would be acting outward. Can you remind yourself, how do you draw a vector that is pointing inward? So inward would be shown in this way, outward would be shown in this way. Do you know why? It's using the right hand thumb rule. So essentially, hold your right hand in a thumbs up fashion, and the way that your fingers curl, that is not your thumb, every finger other than your thumb, if you align it in this direction, then your thumb is pointing outward, right? So that is how you draw an outward vector. And on the other hand, if you had your fingers curled in this way, your thumb would be pointing inward. Okay, so just keep that in mind. We're not sketching it out, but that's a review from dynamics and vector representations. Your objective now is to obtain the equation of motion for this system. Go ahead, pause the video and try yourself. Okay, so how do you approach this? First, you define what are the forces in the spring and the damper, and you always do it for positive x. You have that the force in the spring is going to be equal to what is the net deflection in the spring? This end is constant, this end is moving in by x, which means that the magnitude is going to be kx. And is it going to be in compression or tension? If ever you're unsure, just try to think about it having a spring between your hands. One end, let's say your left hand is fixed and your right hand is moving it inward. What will you feel? You will feel the spring pushing against you, which means that the spring is in compression. What about the damping force? Now, again, for positive x dot, which is going to be in the same direction, there's going to be x dot. So you have to write that as positive x dot. You will have, this is c x dot, and this will again be in compression. In general, you can follow the same sense as what you did for x. So if this here, x is positive, x dot is also positive in this way, which means that this being compression, this will also be in compression. But is that always true? Think about it. These two are independent assumptions. Okay, you can have x being positive in this way, x dot will be positive in this way, but it can happen that your x dot is actually negative at some instance. So you can have a positive x, and at that instance, your x dot would be measured as negative. Okay, if you think about it, if you have x shown here with, okay, maybe I'll sketch it properly. So you have x against time, it's something maybe like this. How would your x dot look? X dot is essentially the slope, right? So here the slope is positive, here it becomes 0, here slope is negative. So if I were to try and do an accurate sketch, it can happen that this here is positive. Let's say it's something like this. Or I guess I should do something like this. And then over here, your slope becomes negative. Here, slope is 0 again. So it would be something like this, perhaps. And it's somewhat close to 0 for some time, and so on. So your x has been positive the whole time, but your x dot was initially positive, then it became negative. So it is possible. But if you're writing your definition as for your assumed positive x dot, then for that assumption, this will be maintained. Okay, all I'm trying to say is this and this, these are independent assumptions, and you have to write them out separately. It's not guaranteed that if this is positive, then x dot would also be positive. It could be negative, as we just saw. Okay, so for positive x, you have this. For positive x dot, you have this FD. Why is it not something like x1 minus x2? Because that's what we defined, right, over here. So x2 minus x1 was what we defined there. The reason is this end is fixed. So if you had called this x2, that would be equal to 0. This here is x1, and it's being measured to the left. In this case, it's x. That's why I have it as kx there. So there's a lot of discussion about the assumption, but it allows you to analyze the system, being fully aware of why all of our statements are as defined. So now I'm drawing the free body diagram. You have a damper, a spring, and the mass. So, how would you draw the directions for the forces? For a spring, it is in compression, which means you're compressing the spring in this way. Why is it that both ends are the same force? It's because a spring is massless. In the same way for the damper, because we assume that it is massless. We then have this here's FD for the damper. So again in compression. Now, because of the way that reaction forces are, they will be in the opposite direction, acting on the mass M. Are we done? Now you have an external force F acting on the system. Okay, this here is your kinetic diagram. Sorry, is your free body diagram. And your kinetic diagram would feature just one element, that is your mass M. In what direction are you going to draw your inertial force? If you did it this way, you are wrong. Why is that? It's because you only look at the direction of positive measurement. Okay, this is a very common mistake, so please be careful when you're drawing that inertial force. It's going to be in the direction of your positive measurement of acceleration, which in this case is in this way. Now, instead of having to always write down your unit vectors and so on, um, since these are just the steps for you to derive the equation of motion, what you could do is you could denote it in your equation itself. You just show what direction you choose as positive. So I'm going to say that this direction is positive. The only thing you have to keep in mind is that you do the same on both sides. So I said that going to the right is positive. Okay, so that means I have now Fs to the right is positive, plus Fd to the right is positive, plus capital F to the right is again positive, is equal to, and on the right hand side you have to the left, so minus mx double dot. Okay, so by doing all of these things, what we're doing is we're defining the magnitudes here and the directions here. Okay, so kind of separating that cognitive load, which will allow you to get the correct answer even in stressful situations like exams and so on. You could skip this, you're likely to make mistakes. You make a mistake, you're losing marks. If you do this, you're less likely to make mistakes. Okay, so let's now write down the values. You have that Fs is Kx, Fd is Cx dot, plus F is equal to minus Mx double dot. If you were to now move this to the other side and write it in the way that I said is the polite or the standard way of doing it, you will have Mx double dot, Cx dot, Kx is equal to minus F. This here is the equation of motion in the standard form. We'll define the standard form more rigorously later, but for now, just trust me that this makes you a polite person. You are representing the system in a way that is standard, so someone who's looking at it immediately knows that, okay, your force F is acting on your system. It has a negative sign, which means that it's acting in the opposite direction to what is your positive sense of measurement. And your system has parameters M, C, and K. So M is the mass, K is the spring constant, C is the damping constant, and these are related in this way with the measurement. Okay, so this is kind of a polite way of communicating your equation of motion. It is expected that you as an engineer would be able to communicate in a way that is effective. And this is how you write equations of motion. Okay, so this equation of motion is a model that mathematically represents how this system would behave. Let's just talk about what would happen if you change this to be x in this direction. What would happen then? If you were to go through the process, essentially your Fs would remain Kx, but it would be in tension. Fd for positive x dot, which is now in this direction, is now going to be Cx dot, but it's going to be in tension, which means that these change in the direction. And so you will have a flip of signs here, and you will have a flip of sign there. Okay, you can go through the motions on your own, write down your equations of motion going through the same steps. Because of this flip of direction, what's going to happen is you will have, in the end, and x double dot plus cx dot plus kx is equal to, and you will have f featuring because your directional positive measurement was in this way. What if you had f acting in the other way? Nothing here would change. Your f would just come in this direction, and then you would have minus f, and so you will have a positive f in this direction in the final equation. Okay, so I hope that's an easy conversation to have. Um, Now, what if we make the system a little more interesting? Let's say then that we have on one end a wall or some rigid body that is fixed and immovable. To that, you have one spring here, K1, a damper, C1, a mass M1, and now we're making a additional level of complexity. So we have another spring, K2, another damper, that is C2. It's connected to another mass of M2. And there are forces acting on the system as well, which is there is F2 of T and there is F1 of T. Okay, so what is the direction of measurement? So in this case, we're marking it, and I should have defined this earlier perhaps, as SEP. So previously we just talked about the equilibrium position, right? We were talking about, this here is the equilibrium position. And that was all that really mattered for the spring. But when you have a damper, your measurements are with respect to the relative velocity. And so you do want to take into account the fact that at this position over here, there was initially no velocity. And so you add a term, which is that it is the static equilibrium position. Because as you know, equilibrium only really means that the net forces are zero. You could have a non-zero velocity so long as the net forces are zero. So when you say that it is static, then it means that there is no velocity at that point. Okay, so that is where the net forces are zero and the system is at rest. So that is the SEP. And I'm going to say that in this case, we have the SEP for both the masses. And in one case, the measurement is to the right, defined by x2, and in one case, it is to the left, defined by x1. Okay. First, can we just think about how many equations of motion are you going to arrive at? Just think through the process. So we applied Newton's law here, right? And we did that for this mass here. We got this equation of motion. If you now do it for this, you have two masses. So you'll have two kinetic diagrams and two equations that you will arrive at. So you need you need two equations of motion to be able to characterize how this system behaves. Okay, and the reason for that is x1 and x2, they are independent of each other. So this could move to the right, and that is fully defined by x2. This could move to the left, and that's fully defined by x1. And so the degree of freedom of this system is 2 because you need both x1 and x2 to capture the system's behavior. Of course, if x1 was negative, then it would be moving to the right. If x2 was negative, it would be moving to the left. But you still need two variables x2 and x1 to be able to capture the system. And so the degree of freedom is 2. This is called 2 degree of freedom system. It's essentially the minimum number of variables you need to be able to capture a position or a state of the system. Okay, so I'm introducing some terms, I'm not fully defining it. I'm just trying to build an intuition for what these terms are. Okay, so in this case, let's start with drawing the free body diagram. Um, let's say for positive x1, what can you write? You can say that this is moving to the left, so this would be in compression. So you can say fs1 is equal to k1 x1. Similarly, for positive x1 dot, you can say fd1 is equal to c1 x1 dot. That is the force in this damper. So it's restoring for positive x1 dot. What about these two springs? I mean, sorry, this spring and this damper. In this case, you have both x2 and x1 affecting them, right? So, well, if both of them are positive, then this spring is definitely in tension, right? So we can say for positive x1 and x2, you can say fs2 is equal to k2 times what would be the net deflection from the equilibrium status. This has moved to the left by x1, this has moved to the right by x2, so it would be x1 plus x2, and this would be in tension. I guess above we should have written that it is in compression. It is also in compression. Similarly, for the damper, you have FD2 for positive x1 dot and positive x2 dot. This is going to be equal to C2 times x1 dot plus x2 dot, and this is going to be in tension. So with that, we have defined the magnitudes. We have kind of defined a directional sense as well. Next, you're going to draw the exploded view of the free body diagram. We now want to go from left to right, defining all of the forces. So in the first case, it is in compression. You capture that first. One good thing about drawing it in the exploded view is that you can always visibly see when you're forgetting any of the reaction forces. So here you have FS1, 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 FD1, FD1, FD1. For this spring, it is in tension. And this one is also in tension. You see how I'm immediately able to capture all the reaction forces as well. It says FS2, 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 FD2, 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 FD2. We've captured all of the forces. Now, there are gravitational forces and so on. Of course, the normal force will cancel that out. So there's going to be gravitational force inward and the normal force outward, they cancel out. Same for this. Okay, we're not sketching it. Okay. Can we now have the kinetic diagrams and then you guys try to obtain the equation of motion? Actually, we did forget something. We forgot to draw the external forces. So there was this here and this here. And now we can draw the kinetic diagram. So we have mx1 double dot in this way, sorry, m1 x1 double dot in this way, and m2 x2 double dot in this way. Now for the first body, sum of forces of the free body diagram of 1 is equal to the sum of forces of the kinetic diagram of 1. I'm going to say that this is positive. I could have chosen the other one, doesn't matter. You can try it yourself, you get the same answer. It's just you'll get negatives, and then when you rearrange it to the standard form, you get exactly the same. So doing this for the first body, I have fs1 plus fs2 plus fd1 plus fd2 plus f1 of t is equal to, and now you have minus m1 x1 double dot. All you have to do now is substitute what is fs1, fs2, fd1, fd2. You have k1 x1 plus k2 x1 plus x2. fd1 is c1 x1 dot. Um, fd2 is c2 x1 dot plus x2 dot plus f1 of t is equal to this minus m1 x1 double dot. And if I were to rearrange it, now I want to capture all the x1 terms, so x1 dot terms next, because in the standard form you go from the highest derivative to the next highest and then the next highest and so on. In this case, x1 double dot came first, so now I'm looking for all the x1 dot terms. You can see there's c1 plus c2 x1 dot, and then there is x1 has both k1 and this here was k2, k1 plus k2 x1, and then I have k, well, I now have only x2 terms, so we start with x2 dot, which is c2 x2 dot, and then for x2 I have just k2 x2. Okay, so here I've captured all of the system parameters and variables, that is x1 and x2, and all the parameters m, c, k, and so on. And then on the right hand side, I will have minus f1 of t. This here is one equation of motion, because we did all of this for just the first block. You now have to do it for the second one. Again, try yourself, choose any direction that you like. I'm choosing leftward as positive. You can choose rightward and try, you'll get the same answer. Okay, so now for this one, I have fs2 is positive, fd2 is positive, f2 is positive, is equal to, now you have minus m2 x2 double dot. If I just substitute the values, I then get for fs2 it is k times x1 plus x2. fd2 is c2 times x1 dot plus x2 dot. And then you have f2 of t is minus m2 x2 double dot. Now again, I'm going to try and rearrange it. I'll then get m2 x2 double dot plus c2 x2 dot plus k, and again I forgot, this should be k2. Have I written it wrong? No. Okay, correct. So this is k2 x2. So now we have the x2 in the highest order, then the next highest, and the next highest. And now you write it for x1. So it starts with c2 x1 dot plus, you then have k2 x1 is equal to, and in this case again you have minus f2 of t. Okay, so this is in the standard form. You have the input appearing on the right side and everything about the system on the left side. So you now have uh, two equations that fully define how this system is going to behave. Um, at any instant of time, this will be satisfied and this will be satisfied. Okay, so we will look at this in more detail now, but I hope that this was a good practice for how you can obtain a mathematical representation of a system.